Looks like we're live. Hello everyone and welcome to yet another recreational programming session. How about it? Let's make a little bit of an announcement and officially start the stream as usual. Red Circle live on Twitch. And what are we doing today on Twitch at a television website? Today we are simulating actual freaking life in C. I feel like I went a little bit over the board with that title, but I think it's good enough. Welcome to the internet in 2023. So I'm gonna give the link to https://tv/todding, and I'm gonna ping everyone who's interested in being pinged. And there we go, the stream has officially started. Hello everyone. Welcome. Really glad to see you all today. So today we're gonna be looking into this paper, right? It's a relatively old paper, right? So it's from 2011, right? As you can see, relatively old, but still kind of relevant. It's a generalization of Conway's game of life to a continuous domain, aka smooth life. Right, so a lot of people probably know what is a game of life. Conway's game of life is this. It's this cellular automaton that actually very simple. It is extremely simple, but it gives the birth to like a lot of complexity. So it has a lot of emergent complexity. And if we Google it up, game of life, right. So and there are some animations I think that demonstrate that. So the game of life by. That's not the game of life I was looking for, actually. That's the wrong game of life, what the fuck? Okay, thank you. Thank you, DuckDuckGo, very cool. Every time I want to switch to DuckDuckGo, shit like that happens to me. Anyway, so Conway's game of life. Right, so you can see this like a lot of different interesting complexities. So this is basically Conway's game of life. This thing is just like a shooting gliders, and a glider is probably the most like interesting structure that emerges out of the Conway's game of life. Right, so but this paper is about actually taking this discrete thing and generalizing it to a continuous domain, as it basically says, right? So, and it looks actually kind of spectacular, right? If you Google up smooth life, right, smooth life, it's actually kind of cool. It's just like game of life, but it's actually like very continuous, and it creates this sort of like, you know, biological like structures and everything. It's just actually freaking spectacular. Right, and it's not on a finite discrete grid. It's actually continuous, right? So in game of life, the cell can be only in two states, 0 or 1, dead or alive, right? So this thing, in this thing, the cell can be in any state between 0 and 1. So its state is continuous. Right, its state is kind of continuous, right? So, and it actually creates, it has its own gliders, right? It has its own gliders that look like this, right? And they are, unlike the game of Conway's game of life gliders, they're omnidirectional. So that means they can move in any directions, or not only diagonally, right? So, and I think that was the goal basically of this paper, is to just come up with the sort of like a Conway's game of life that creates omnidirectional gliders, right? So, and the problem with the smooth life, right? The problem with smooth life is that it feels a little bit gatekeeping. I don't think it's intentional, but you can quite easily just look at the Wikipedia page of Conway's game of life and get an idea on how to implement it on a computer, right? And that's what made it so popular. That's what made it so popular, because like anyone, even without any like mathematical background or anything, just like can open that page, read that page, and understand what the fuck is going on. This thing, you open this paper, and the first thing you're greeted with is the freaking integrals. What the fuck is this shit? Like, what the hell? It's just like, no, like, it's just like everyone is gonna be scared away from that, but I do understand where they're coming from. I do understand where it's coming from, because it's a continuous thing, right? It's a continuous thing, and they need to describe continuous sums, right? So, and that's why it just goes here, and it's a little bit scary. Like, what the fuck is going on in here? It's not like Conway's game of life, where you can have a description of about the paragraph, right? And there you go, that's enough for you to implement that. Like yeah, you need to understand what the fuck is going on in here. And that's why not that many people actually implement this thing. There are some implementations of this kind of stuff, but it's not like Game of Life where anyone on any machine with any programming language can just like sit down and implement this entire thing, right? So it's kind of like a, yeah, it's a bit gatekeepy, but I don't think it was intentional. So, and the cool thing here is that if you manage to implement it, you would start seeing these kind of structures, and that's basically the glider that we're looking for, right? So it's an omnidirectional glider. So in this case, I think it's going to be moving in that direction. So it moves towards the thickest part, right? So this thickest part actually moves there. And notice how fuzzy it is. Right, notice how fuzzy it is, and this is because like each pixel is kind of a cell, right, and the cell is continuous from 0 to 1, right, and that's why it's might be fuzzy on the edges, because these cells are in the transitional states or something like that, right? So that's basically what's going on in here. Right, so luckily this paper is actually very small, right? So even though it's kind of like starts with the integrals, it's just 4 pages. I read the entirety of this paper. I kind of understood majority of the thing they were trying to convey, except a couple of things, but I think we can try to ignore them, right? So my goal for today would be to try to implement this thing at least in a console. Right, at least in a console, and see if we can simulate this thing in a console and produce interesting patterns. And if we have enough time, we may try to port that to GPU, to a fragment shader, because I think from what I understood by reading this paper, so it's actually relatively easy to port to fragment shaders, right? So essentially you can store the state of the cellular automaton in a texture. Then you can have a shader that computes the next state into frame buffer, and then you can reuse it again as a texture and sort of like progress by doing draw calls. A single draw call is going to be basically computing the next state of this cellular automaton, and since all of that in parallel, it should be like super fast, and I think that would be actually kind of cool. Right. So some people actually pointed at Linea, right? Linea. So this is another interesting thing. I think it was actually done relatively recently, right, in 2018, right, or somewhere. It's relatively recently, and it's basically continuation of the idea of smooth life. Right, if you actually take a look at the paper on the Linea, I don't know how to pronounce this thing, by the way, Linea paper. So, it's even more scary than this, right? It's even more scary than this. I'm gonna show you. I also partially read that paper too. I couldn't actually do it to the end because how complicated it is. Right, but the cool thing about that paper, right, the cool thing about that paper is that what they tried to do, right, so they tried to do something different. The smooth life, if you take a look at smooth life, you can treat it as a framework for defining continuous cellular automatons, right? So what they did there, they said, okay, so that framework has different parameters, right? This framework has different parameters, and they also edit their own parameters, and they ask a question, okay, so to weaken that parameters, can we come up with interesting creatures? Like how many interesting creatures we can come up with if we just like tweak those parameters. And what they did, if I understood correctly from that paper, they made an automated system that basically brute forced different parameters of the environment and used artificial intelligence to basically recognize the patterns to capture the most interesting creatures. And they managed to categorize around 400 different creatures. Like they managed to identify them. Right, and there is a lot of interesting creatures in here. So we're not going to be doing that today, but it's just something interesting to keep in mind. This is what people were doing with this kind of idea. Right, so this is basically different creatures that they managed to actually capture and categorize, right? So there are some interesting things that spin around. Right, so this is like different kinds of gliders. Yeah, this one. So these kind of things, they actually spin around. So yeah. So the cool part of this specific paper is that they had to build an automatic system to actually capture those creatures, right? So they didn't do that manually, right? They didn't do that manually. They did that automatically. So that's what's cool about it. So they also, there's like a last, I think, page somewhere where they actually compared some of the found creatures with the real life creatures and found similarities, right, between like single cell creatures in real life and what they found in this thing. So it's also kind of cool, right? So I'm gonna put both of the papers in the description, of course. So first paper, the one that we're gonna be doing today, right? It's the Smooth Life and basically Linnea. I hope I pronounced it correctly, right? So it's gonna be this one. So Smooth Life paper, Linnea paper. I'm not sure if today's stream is gonna be interesting enough and we get somewhere. Maybe we can try to implement Linnea. And we'll see how it goes, right? So, but it's probably not going to be on today's stream, right? So it's probably not going to be today's stream. So here I actually gave the PDF, so let's actually give the actual PDF in here. All right, so we've got some subs. We've got some stuff from Marks77. Thank you so much for Twitch Prime subscription. Thank you, thank you, thank you. How are you guys doing? Hello, hello, hello. Cool idea of implementing papers. Yeah, it's actually kind of cool. Though sometimes it's kind of hard to like find interesting papers, but I don't know. Paper review, right? Imagine paper review series from Zozin, right? Where I take a paper and I implement it on a stream from scratch in C. That's an interesting idea, actually, right? But I'm not sure if I'm smart enough to do any paper. It was kind of hard for me to read this thing already, so I don't know how it's gonna go, right? So we got another sub, Junior Fretas. Thank you so much for tier 1 subscription with the message "Tsodin sleep, Tsodin sleep, Tsodin sleep." I hope this is not because the stream is boring, but thank you so much for tier 1 subscription. Let's knock things off by implementing like maybe a simple C program, right? So I want to implement like a renderer, the terminal renderer, that would allow us to actually, you know, display the state of Smooth Life, right? So in case of the game of life, you just have two states, 0 and 1, but here we have a continuous state from 0 to 1, so we have to actually display that somehow. Like, I don't want to start with a complicated renderer with like using graphical library or anything like that. I want to just start very, very simple. Right, so how we're gonna do that? Let me actually go to Zozin, and I'm gonna create a folder, Smooth Life. There we go, and I'm gonna open main.c, and let's just like implement a simple hello world. Right, so this is gonna be printf hello seaman. All right, and let's do build.sh, and let's do bin.sh, and let's simply build this entire stuff. Main.c. Let's also enable all of the warnings, all of the extra warnings as well. Let's make this executable, and let's build this entire scheiße. Okay. All right. So for those who doesn't know, Hello Seaman is basically a reference to John Blow constantly writing Hello Sailor, right? So it's sort of like a theme related to, you know, seas and ship, and I decided like why not basically follow his advice and say Hello Seaman as well. Yeah, so I think it makes sense. Okay, so let's define a grid, right? Let's define some sort of a grid. Let's actually define what kind of like size of the grid we're going to have, right? So let's make it 10 by 10, right? And let's initialize that grid. So this is going to be, of course, height. And I start with the height and then width because the way C stores the multidimensional arrays, right? Because of how C stores multidimensional arrays, it stores them row-wise, right? So, and essentially this is basically the rows and this is the columns. Even though it's width and height, I think about this thing in terms of rows and columns, right? That's why I prefer like putting height first and width second, right? So because I think about how it's located in the memory, right? So when I'm writing the code, I actually don't see the text, I don't see the code, I see the memory layout, believe it or not, right? So I just like visualize the memory layout, and that actually dictates a lot of like decisions that I make in my code, right? So because of how the arrays are stored in the memory, I prefer to first define the you know, the rows and then the columns. It's a matrix, right? So it's a matrix order basically. So I think they do the same thing in math, right? So because in math the first index is the row and the second index is the column, right? So anyway, since it's a continuous thing, it's going to be grid of floats, right? So this is a grid of floats, and let's actually initialize it with zeros. So one of the things we probably want to do, we want to basically initialize this grid with random bullshit, right? So let's actually iterate by y, right? So this is going to be y, iterating height plus y, size t, x. It's gonna be less than width, so this is gonna be that, and essentially I want to have like a random float from 0 to 1. Well, I think we already implemented this kind of thing in nn.h, right, in our deep learning framework in C, but I can implement it one more time because it's such a simple function, right? It's not worth like copy pasting or going anywhere in there. Right, so essentially rand, there is a rand function in C, and it returns a value from 0 to rand max. So, and essentially what you can do, you can cast both of these things to float and divide the smallest things by the maximum thing, and you will get basically a ratio from 0 to 1, and that's basically like everything that you need to have in here. Right, and after that we can try to maybe print the state of the board, the state of the grid, just to see what's in there. Right. That would be kind of nice to see what kind of values we managed to generate there. Right, so this is going to be printf, and we're going to do f grid yx, and then here at the end I'm going to put a new line, and there we go. Let's take a look at what we've got. So first I'm going to rebuild this entire thing, and I'm going to run this entire stuff. Rand max is not available, everything is broken, nothing works. That's why you have to program in JavaScript, because you never have to compile, so you're never going to have compilation errors, even though you're going to have runtime errors, right? So, but who cares? At least you're not going to have any compilation errors. So here we just need to include stdlib, right? So, and there we go. So here is random bullshit. So this is a random bullshit. So, but it's not particularly random because we also probably want to, you know, set the seed. We want to set the God seed. Right? We're setting the God seed, and there we go. It is different every single second, right? So every second a God seed is renewed, and this is because the time function returns the current seconds since the Unix epoch, right? From 1970-0101 or something like that. I think this is how POSIX system actually store the time, but I'm not a programmer, so I don't really know. So essentially, how can we visualize that? How can we visualize? That's a very interesting question. Like, we don't want to visualize our shit like this. It doesn't make any freaking sense, right? So one of the things we can do, we can treat these values as the brightness. Right, we can treat this value as the brightness, and essentially we can quantize that brightness. We can quantize that brightness. So essentially we can have some sort of like table of levels, right? So this is going to be a level, and essentially the brightness with a very low brightness is going to be denoted by simply a space. That makes sense, right? So a slightly higher brightness, right? A slightly higher brightness is going to be denoted by dot. Makes sense, right? Makes sense. Even higher one, probably underscore, right? So even brighter, so here is just like a one single line. Let's put 2 lines, it's going to be equals. So then maybe even brighter is going to be like a letter. Let's put it like C, right? So it's even brighter. Something even brighter is like C, but closed, it's going to be O, right? And then we can keep making it more and more dense and dense, right? Dense and dense. And essentially what we've got here a gradient. So here maybe I want to actually use like a dash, right? I think dash makes a little bit more sense, right? So as you can see, they come from less dense to more dense. Right. Dense, not dance. Like, I don't know how to speak English, I'm sorry. Right, and essentially we can use this entire thing as basically the table for the levels, right? So, and if you have some sort of a brightness, right? So imagine that you have a grid, right? You have a grid of this specific value. How can you determine what kind of character you have to replace it with? You need to take an interval. You need to take an interval from 0 to 1 and divide it by the amount of levels in here, right? So let's actually do the following thing. All right, so this is going to be 1, and divide by the levels size, right? So maybe levels count. So this is called actually levels, so let's go level, right? So, and this is going to be a continuous thing, and basically it will tell you the segment, right? So the segment, and then by essentially dividing your entire thing by that segment, you get an index in that table. Right, and so what's interesting is that if you actually simplify this entire expression, you're going to end up with just multiplying grid by the level count, right? So, and you can already use this as an index within the level, but you have to be a little bit careful, right? So you probably want to do something like -1, right? Because the grid equal to 1 will make this entire expression equal to level count, which is the out of bounds for this specific array. Right, so which is out of bounds, so you probably don't want to do this kind of shit. Right, and then you probably want to truncate it by converting it to an integer, and then you'll be able to just like take this specific level, right, so, and then just print it, right? So let's actually try to do something like this. Right, so we don't have a level count, right? So let's actually maybe do something like this. Maybe it's going to be something like that. So if I do size of level divided by size of level 1, I'll get the amount of elements in this specific array, which is actually going to be kind of not correct. You'll see why. So let me just print the amount of levels that we've got in here, right? So I'm going to do something like printf. Right, so this is going to be 0. So level count equal to that, level count. And let's see how many levels we've got, right? So this one has to be something like this. 11, right? But is that true, right? If we try to count how many characters we have in here, it actually says that we have 10 characters. So what's going on? Right, why trying to do something like that actually yields 11 characters, but here we have 10 of them. Right, because this is a string literal, and string literal has an implicit 0 at the end of it, because welcome to C in 2023. Yes, that's right. So that's the actual reason. Welcome. This is the most beautiful language on planet Earth, Kappa. Right, so, and this is something that you have to be aware of. This is something that you have to be aware of, and just do -1, right? So if you are initializing array of characters with a string literal specifically, it's going to be like that. So what's fun is that if we initialize array of characters like character by character, I don't think it's going to be the thing. So can I query replace with a regular expression where I can say, okay, single character has to be replaced with, single character, which is also captured, because we'll need to be able to recreate that. Also replace this entire thing with the original character and also comma. Will I be able to do that? Can your Vim do that? I don't fucking think so. Yo! There we go. Vim can do that, I know. Thank you very much. Alright. So, if you initialize this entire thing like this, right, so it's gonna be 10, right? It's going to be 10. It's going to be correct. But if you do it like this, it's going to be 11. All right, so you can also specify the byte size like this. It says the chat, right? So this is the message, like I'm not making it up. And then when I add another character in here, I should not forget to increment this thing. So maintainability of the code decreased dramatically because to add a single thing, now I have to modify 2 places. Thank you very much. No, I'm not going to do that. So now, yeah, so essentially what we're going to do is just like -1. Right, so simply -1 and everything is okay. So we have a convenient way of defining this entire stuff, and there we go. So we're good to go, we're Gucci to go. So, and the only thing we need to do in here is just like literally print this entire thing, right? So just literally print this entire X, and let's see if it works at all. It doesn't freaking work. Let's find out why. So array subscription is of character, doesn't really. So I suppose I have to wrap this stuff around. There we go. So something kind of worked, but at the same time, as you can see, this is, yeah, that looks weird. That just looks weird. And oh yeah, so I suppose I see what's going on. I see what's going on. Now we go. Yeah, as you can see, now we have a random noise. So this is basically a random noise. That's pretty cool. So on top of that, we can make it a little bit bigger. So what about 100? So this is basically, yeah. So Emacs wants to highlight some shit in here. I don't know why, but yeah. So because it automatically recognizes some of the patterns in here, right? So because it wants to maybe parse some things to make it more like readable and stuff like that. But there we go. So now we have a thing that allows us to display the continuous state of the board, right? So now we are able to display that continuousness and stuff like that. Now we need to understand, how do you even compute the next state, right? So how do you even compute the next state? So in original Game of Life, the next state is computed by looking at the neighborhood, right? So you basically count how many alive cells you have, and based on the current state, on your current state, and how many neighbors you have, alive neighbors you have, you make a decision either to stay alive, or to die, or to get born, and so on and so forth, right? So that's basically what decides the transition. So here we have everything continuous, right? Here we have everything continuous. So in the neighborhood of the cell is described by these 2 integrals, right? Which are kind of scary, but in reality they mean a ring. All right, so essentially, let me actually open up my paint. So let me actually open up my paint. So imagine that this is an infinite board of a smooth life, and we're trying to compute the next state of that specific point, right? So essentially what we do, we look at the circle around this entire thing, and this has a radius, which is called Ri, which is the inner radius of the ring, right? So this is the inner radius of the ring. Then we have outer radius of the ring, so the outer radius of the ring, like this. I can't draw this shit. Okay, let me try to do something like that. It's not particularly even radius, right? But it is what it is, and it isn't what it isn't. I apologize for that. So anyway, so this is basically the outer one. The paper denotes that outer thing as RA. So I is inner, that's why it's I, and A is outer. I don't know why it's not O, but maybe because outer. I don't know, maybe that's why. Essentially, right. So, and you have to keep in mind, so this is basically, you have different cells, values of the cells in here, and you have different values of the cells in here. So what you do, you literally iterate through all of the cells in the inner circle in here and the outer one. So if I remember correctly, the inner one is called, yeah, they called M, right? So basically M is the sum of all of the values inside of this thing, right? So this is inside, and N is basically the sum of all of this thing on this outer ring in here, right? So, and what's interesting is that instead of the sigma, I think this is the sigma, so the sum is denoted by sigma. They're using an integral symbol. And this is because they want to imply that it may happen on a continuous space. Right, but since we're working with computers, right, which are digital computers, discrete computers, and we can't really model continuous things on such machines, right, so we're going to be using like an actual sums, right. An integral just, it's basically a sum, like it's basically a sum, but it just implies that somewhere in this hypothetical world where we have, you know, rainbows and ponies and stuff like that, it's gonna be continuous and it's gonna be so fucking smooth. It's just like, holy fucking shit, you're gonna fucking come. But in real world, we can't afford. Right, so... So what I'm trying to say is just don't be scared of this integral, right? Because in reality, it's just a fucking sum of the points around the current point. So that's what it is. Hey, welcome to the paper review with Zozin. Okay, so I think we've got a bunch of subs that I need to acknowledge. All right, so Gaetan Florio, thank you so much for a tier 1 subscription. Shmoky Bear, thank you so much for tier 1 subscription. And Johnny DeResta, thank you so much for Twitch Prime, 13 month, more than a year, with the message, yo, hey yo, my friend. Alright. My eyes with the white, oh, I mean, we can just download this thing. Okay, so, if you don't want me to flashbang you, freaking, do you want me to just save this entire thing? Like, I mean, they banned wget. That's what they did for no freaking reason. I don't know why. All right. So yeah, so the archive be like that sometimes. So let's actually move this entire thing in here. So this is gonna be this one, and there we go. So here is the paper. I'm gonna open a new PDF and I'm gonna invert it. Is it better now? Is it better? So this is our paper now. So I'm gonna close this entire thing. Right. So yeah, it's kind of difficult to read. If I could make the background more like grayish rather than black, I think it would have been like less harsh on the eyes. Black is a little bit too strong. Right, and essentially, what you can think of these two values, right? So m is the sum of the values, literally the sum of the values in the inner circle, and n is the sum on the outer circle. You can think of these two parameters as basically the amount of dead and alive cells in a Conway's game of life. Right, so in Conway's game of life you have actually you have your current state, the amount of death, the amount of life, and based on that you make a decision where to transition, right? So, but in this thing, you make a decision based on that, right? And based on these two values. And how do you make a decision? You have a very smooth, continuous function, which they call here, I think S, yeah, so this is basically S. Right, so this is basically S, and you feed these two parameters into this function, and that function tells you the next state for the current thing in here. That's it! I'm not even fucking joking. That is fucking it. Almost, right, almost, so... right, so, and we just basically we have to do, like, we have to iterate through each point, consider this neighborhood of the rings, right, and compute the next state for them. Like, it's the same way you would do, the same thing you would do for the Conway's game of life. It's just like the function more continuous, more complicated and stuff like that. So what's going to be this function? Well, this function, okay. So if you want to take one variant of the definition, so essentially I think you can use different functions, but they have to be like, have a certain property. One of the functions that have this property is this one. Right. So S is going to be defined as composition of these three functions, right? So you see, this is a composition of these three functions, and here are these three functions. But I mean, you don't have to understand them. Like, do you? Do you really need to understand them? You can treat them as black boxes. So just like, yeah. So the actual framework here is that you like basically take these two parameters and you have this magical blob from the vendor of the paper. You feed this data into this proprietary blob, and it spits out the next state of this thing. Right, we do that all the time with the NVIDIA drivers, so, and everyone's fine with that for some reason, but when it comes to papers, everyone is just, oh, gatekeeping. I mean, it's just like, it's a binary blob, what did you... You know what I mean? It's just like... What's interesting is that some people notice that it's a sigma. It's actually sigmoid, right? It's actually very close to the sigmoid that is used in artificial intelligence, machine learning, and neural networks. The actual definition of sigmoid that is used in there, I think, just minus x, right? So it's 1 divided by 1 plus exponent minus x. But as you can see here, they actually introduce a bunch of parameters. So I suppose to shift the sigmoid around to some sort of like a state or whatnot. Also, it would be cool to try simpler function. Yeah, that would be actually kind of cool. As far as I know, they say here that none of that like smoothness is really needed. Right. So I don't remember where they said that, but yeah. So, and essentially, you also want to make a smoother transition. In terms of like a time, because essentially what you get in here in reality, you don't really get like a step. You get the next state of the state on the next second, right? So if you measure the time in seconds, you get the state on the next second, or let's say on the time on the next unit of time. But what if you're running with 60 FPS and you want to actually do like step 16 times within 1 unit of time, right? How would you write that? So essentially they say you can treat this thing as actually a derivative of the function and basically the direction in which you want to move the current state. And you, instead of like setting this as the next state, you can just add this thing multiplied by delta time and it will work as well. Right, so that's essentially what they say here, right? But one of the things you have to do, you have to map its value from -1 to 1 to 0 to 1, or the other way around, but whatever. Okay, so let me see. So we got some subs. Let me acknowledge that. Xerza, thank you so much for a tier 1 subscription. Thank you so much for tier 1 subscription. Okay, go. So we'll go ahead and try to implement that. So, and as you can see, there is a lot of parameters in here, right? So there are radius and stuff like that. And this is one of the things you can try to tweak, right? And experiment and see what kind of creatures you can come up with, right? So, okay, go. So let's maybe define the outer and inner radius. As far as I know, in the paper, they just say that you can only need to define the outer, like inner radius, because the outer radius is going to be like, yeah. So essentially, you define the inner one, and the best result you can achieve is just basically multiply it by 3, and here is the outer radius, right? So that's basically it. So that's pretty cool. Okay, so let's define the RA, and let's say, I don't know, so they have some example at the bottom, right, so they have some example at the bottom. So here they say the outer is going to be 21, right, I don't know, so they basically suggesting that we want to define the outer one first and then compute the inner based on that. I mean, sure, let's actually define it the other way around. So this is going to be 21. So essentially, they achieve this glider by using these parameters in here, right? So, and maybe this is the parameters we're going to be using in here, so why not? Okay, so what I want to be able to do, I want to be able to compute this n and m for a particular sort of point on the grid, right? So I want to be able to do this kind of stuff. So maybe I'm going to actually factor out some of these things in here. So here is basically a random initialization, right? So it's actually called random grid, right? So this is a random grid. And I'm going to literally move this entire stuff in there. Let's just factor it out, random grid, right? And in here we have a basically procedure that displays the grid, right? So let's actually do something like display grid, right? And we'll just move this stuff in there. So displaying the grid, display grid. Cool. So, and as we generated the random grid, so what I want to do, I want to just like basically define maybe like a point, right? So let's actually say that I'm going to have x, which is going to be like 0, right? And y is also going to be 0. And that's the point for which we are going to be computing m and n, right? So initially they're going to be 0, right? So initially they're going to be 0. Right, there we go. So what's going to be the next thing we're going to do? What's going to be the next thing we're going to do? I suppose we just need to iterate the whole circle, right? So we just need to iterate the whole circle. So essentially what we can do, we can just iterate the enclosing cube, a square of this thing, right? So here is the current point, x and y, right? Here is its outer thing. Here is its outer thing. We can construct a square that basically encircles this entire thing and iterate pixel by pixel this entire thing. And if the point is within the circle, we're going to consider it. If the thing is outside the circle, we're not going to consider it. And then we can even try to check, is it within outer circle or inner circle? And depending on which circle it's in, we're going to actually add it to either m or n. Right, so that's basically how mechanically we're going to be doing the integration, right? So that's basically what we're going to do. So that's my idea, at least for now. All right, so and that is determined by the radius, right? So let's actually maybe start an iteration, so size t, and we're going to actually iterate with dx, right? So this is going to be dx and dy, right? So we probably want to start with minus ra, and dy RA, right? Something like that. So essentially, let me think. So if RA is equal to 3, right? If RA is equal to 3, we are located somewhere in here, right? So we're located somewhere in here. We can do 1, 2, 3, right? And we're starting to iterate, so from somewhere here. And this is not particularly what I want in here, right? Because this entire thing doesn't have a radius of 3, it has a radius of 4. So that means what we probably want to do, we want to actually iterate maybe like -1 up until this thing. Right, and if we did something like less, we wouldn't have to do -1 in here. So, and essentially the reason why I want to do it like that is because then I will be able to just say y plus w, and that's going to be like the actual point on the grid that I can consider and just do something with, right? So I suppose that kind of makes sense. So we want to do a similar thing for dx, right? So this is going to be for dx, and there we go, right? So this is what we're iterating, and then right, so maybe it would make sense to actually call this thing Cx and Cy because it's a center. And since this thing can be negative, I think it's not a good idea to actually use size because it's unsigned, right? So we want to actually use integer which is signed, right, because we're going to do signed arithmetics and stuff like that. Right, so, and let's do the following thing. We're going to create Cx plus dx. Y is going to be cy by dy, and there we go. So, and that basically tells us the actual thing on the grid. But here's an interesting thing. So if you are at the left top corner, right, if you're at the left top corner, this thing might be out of bounds, right? How do we handle out of bounds situation with this kind of stuff? So essentially we can just wrap it around, right? We can wrap this entire thing around. So usually to wrap things around, people use mod, right? So mod is a very useful thing, right? Essentially, if you have the width equal to 1, or to 100, right? And your x is 101, you can just do mod and it wraps it around. And as you go further, right, so it just keeps wrapping around. And as you can see, then if you go to 200, it wraps around to 0 again. Right. So, but as far as I know, it doesn't work the other way around. I think in Python it does work if you do like -1. Yeah, in Python they actually specifically fixed that, but it doesn't work like that in all of the languages. So in Node.js, if you try to do something like this, if it starts up at all, -1 and mod 100, you're gonna end up with 100. So usually the usual way to fix all of that is basically add the thing that you're modding by. And that, as you can see, fixes that. But that, on the other hand, breaks the positive case, right? So as you can see, positive case doesn't work anymore. And for that case, you do mod 100 again, right? So in that case, negative case works and positive case works. So that's how you do that, essentially. Right, so as far as I know, in Rust, this kind of mode operation is called Euclidean mode, and because of that, I like to create a function called emode, right? So, and in emode, you basically have two things in here where you just literally do divided by b, then you fix the negative case, which breaks the positive case, and then you fix the positive case again by doing something like that, right? So, and once you have emode, so you can essentially do the following thing. So we have something like this, and then you can say emode width and emode height. And there we go. You can be 100% sure that x and y is going to be within the boundaries of the grid. Right. So it's going to be within the boundaries of the grid. Right. So, and let's, and then you can just basically do the following stuff. So now we need to see whether this entire thing is within the inner or outer circle, right? So how can we even do that? So we have an outer circle, so an inner circle, so is going to be RA divided by 3, right? So that's basically the inner circle. So okay, cool. And so we need to know the width of this entire stuff, right? The width and height. Interestingly, believe it or not, we can already use dx and dy to determine whether we are within the inner or outer thing in here. So we can just literally use dx, the square of dx, then the square of dy, and then sqrtf, and that gives us the length of the current thing, and we can already consider it. So if it's, for instance, less than the inner circle, we are within the inner one. And where is this thing? So let's actually go back to the integrals, right? So we have to add it to m, right? So we have to add this entire thing to m. So, all right. So m plus grid, so I suppose we'll have to pre-compute this stuff anyway, y and x. But here's an interesting thing, right? Here's an interesting thing, so maybe we want to also make it equal. If we raise both of the sides to like a power of 2, we don't have to call to square, effectively making it a little bit faster, right? Because square root is actually kind of a heavy operation, right? So, and then the next thing we can check, right? Otherwise, if this entire thing less than the outer one, right? And since because it's else, we know that it's bigger than this thing. So here we know that it's between the inner and outer circle. We have to add this entire thing to essentially grid y x. There we go. And yeah, there we go. So essentially we compute this entire thing for the point 0, 0, right? So we can now print this entire stuff. So m is going to be equal to that, n is going to be equal to that. So m and n. There we go. So, and do we even see anything? So I think I want to remove this entire stuff, right? So I want to remove this entire stuff, and there we go. Right, so we get these two parameters. But here is the interesting thing. There is some sort of divided by m and divided by n for these values correspondingly. And this is what the paper says about these things. N and m are normalization factors, such as that filling is between 0 and 1. So these values have to be between 0 and 1. How can we even achieve this kind of stuff? So essentially, when m is going to be equal to 1, when each individual point within the inner circle is going to be equal to 1. So that means m is the area of the circle, of the inner circle. And n corresponding is the area of the ring, of the outer ring in there. Right, so essentially we have to sum up all of the, sum of all of the values within the circle and divide by the area of that circle to normalize it to a value from 0 to 1. And the same thing has to be done in here, because they're going to be equal to 1 when each individual thing here is equal to 1, aka the surface of the circle. Does it make sense? So we can try to, you know, bust out the formula for computing the area of the circle, right? We can do that, right? But I'm thinking about a more interesting thing. What if we literally count how many pixels we have within those things? So essentially, just a second, we can literally define big M and big N. I mean, technically, it's going to be an area, or something very close to an area. It's going to be something very close to an area. So when we do plus, like m plus this thing, we can do plus 1. And here, plus 1. And effectively, I mean, I'm not a mathematician. I'm an engineer, okay? I'm an engineer, so whatever fucking works, it works. Right? So this will work. We know that it will work. It doesn't have to be elegant or pretty, whatever the fuck mathematician came up with. It's just, it works. Fucking works. Just duct tape that shit around, it freaking works. Anyway, so... so if we take a look at these things, right, so these are the values, right, and then, right, so it's actually different every time because we randomize the thing. So essentially what we can do after that, we can just divide this stuff by, like this, right, so... It's so good not to be a mathematician because you can do shit like that, right? I'm not a mathematician, I don't know. It works. Right, so let's actually see if these values become from 0 to 1, and they are. Look at that. They are from 0 to 1. It fucking works. So what do you want from me? It works. It freaking works. So... I think it is elegant and pretty though. It correctly normalizes the discretization of the... Oh yeah, that's actually true. If I used the formula of the area of the circle, it would actually be a little bit bigger because it will include the area. It doesn't take into account the quantization and stuff like that. So it will have this extra like corners that slip in there. Yeah. Okay, this is even more correct than using this... God damn it, that. Engineers won again. Anyway. Thank you so much. Anyway, so we got that shit, and essentially what we have to do, believe it or not, chat, we have to plug that thing into this crazy blob, like a vendor blob, that comes with this paper, right? So the paper comes with the proprietary blob, and we can plug this entire stuff in there. So what's interesting is that there's something that bothers me about this paper, right? So one of the parameters of this function is alpha. Everyone can see this alpha, right? So here's the alpha. So it's that. Okay, so what did they say about this alpha? The width of the step is given by alpha. Okay, so that's the width of the step, whatever the fuck step means, I don't know. As we have two different types of steps, we have AND and AM. What? Where is A? And the only other place that they mention AN and AM is at the end of the paper, where they say, okay, so if you set AN and AM, you're gonna get this glider. And that's it. It's never mentioned anywhere in the paper. It's never mentioned in any of the definitions at all. And it was like, I was reading this paper, I was just like, bruh, what the fuck? Like, it's just like, you define some parameters, but you never use them. You used alpha without the subscript. It's just like, what? Maybe they are referring to something in one of those papers. Maybe something... By the way, I read some of these papers, by the way. Have you guys seen real life paper? Have you guys seen real life? So, you think freaking integrals are scary. I'm gonna show you real life paper. Like, a real life paper. You thought that the linear paper is fucking scary. Look at that shit. Just a second. Yeah, continuum limits larger than life, blah, blah, blah. I'm gonna show you something. I'm gonna freaking show you. All right. So, just a second. So, first of all, notice the size of this paper. 34 pages, right? So, this is 34 pages. I'm gonna actually zoom in on this shit. So, it has to be, like, it's gonna be white. I'm sorry, so I'm gonna flashbang you a little bit. But here's the paper. This is the 34 pages of this. Don't worry, it gets worse. It gets worse. 34 pages. I'm not even sure it's written in English, honestly. Ah! Holy fucking shit. It doesn't stop, like, that's the funny part. It doesn't fucking stop. So we are on the 21st page. There's 34 of them. Anyway, so I'm gonna give the link to this entire thing. So, look, but personally, to be fair, proof by intimidation. Yeah, it's a proof by intimidation. I personally didn't try to read this paper, in all fairness. Maybe, if you try to read it, it actually makes sense. Right, so real life. So the thing about linear paper is that it looks a little bit intimidating, right? But if you actually sit down and just ponder upon the formulas and definitions and stuff like that and connect pieces together, it makes a lot of sense. In fact, I managed to understand smooth life paper way better because I tried to read the linear paper first. I tried to read it, follow definition, and it sort of like helped me to understand, like, get into the mindset of people who work with these continuous cellular automatons, and it helped me to understand this thing better. Right. So just because it looks intimidating doesn't mean that it is. Maybe it's incredibly consistent. Maybe it's so perfect it doesn't have any logical errors, and that if you actually follow through this entire thing, it will make perfect sense. The worst part about this kind of stuff is that you may have something extremely intimidated, but at the same time you have errors in here. Right. And because of that, you may not even know that did you not understand something or the author made a mistake, and you may never know, and it's just extremely frustrating. Maybe this paper is so fucking perfect, maybe everything is double checked by a computer, by the Cox system, you know, the proof assistant and stuff like that. It's so fucking perfect, if you just like sit down and follow it, it makes perfect sense. I don't know, I never tried that. So basically, yeah, so... just saying that just because it looks intimidated doesn't mean that it's impossible to understand. It just like depends on the quality of this thing, but I don't know the quality of this thing. Right. Coq assistant. I meant cock. Oh yeah, this thing, yeah, so it's a proof assistant, it's not a cock assistant. It's a basically thing where you can write theorems and prove them automatically. It's actually a pretty cool thing, so I want to learn it properly at some point in the future. Right. So yeah, let me actually put this stick in here, cock assistant. Okay, so this is a cock assistant. Learning cock. So to be fair, this language has a very cool clickbait value, right? So you can just put learning cock in the title and everyone, haha, cock, ah, I'm 13, oh, funny, funny. So it works. Alright, so we're doing that for an hour already. So I would like to make a small break because I want to make a cup of tea. And after a small break, and after I make a cup of tea, we're gonna continue and we're gonna try to actually like feed these two values into this proprietary blob and see where it will take us. So yeah. So let's go ahead and try to implement that monstrosity of a function. Right. So where is my sigmoid? So this is the first sigmoid. So we have sigma 1 and sigma 2, right? And sigma 2 is defined in terms of sigma 1. And we also have sigma m, and we also need to define sigma balls. Fucking. All right. So we have sigma m, right? And s, the transition function, is already defined in terms of, I guess, not really all of them, but sigma 2 and sigma m, right? So let's first code the sigma 1, right? So I think that makes sense. So this is going to be sigma 1. I'm going to even split my screen in two, so it's easier to copy-paste stuff. So this is a sigma 1. It accepts x and it accepts a, and it's also parameterized by alpha. Right, so, and I suppose, and I hope this is not a typo, right? So, because you have A and alpha, I really hope that it's not a typo, so they didn't confuse this kind of stuff. Though, if they used later, right, if they used later, if you want to type A, you would just type A, and if you want to type alpha, you would have to do something like this. So, it's kind of difficult to put alpha accidentally, if you know what I mean. Right, unless it's a logical error, but I doubt there's any logical errors in here, at least like obvious ones. Except this part with alpha n and alpha m, I'm not really sure what the fuck are those things and how they're supposed to be used, but I don't know. Maybe people who understand this paper better can point out like what the fuck they mean by these things, but I couldn't understand that. So, right. I feel like alpha n and alpha m refers to the things that you can plug in here. But when do I plug alpha n and when do I plug alpha m? The paper still doesn't kind of answer that question, so I'm going to basically assume that there's only one alpha, right? So, and we can always play with those parameters and see how all of that goes, obviously. Okay, so let's actually start with expf. Don't decrease that much, please. Minus x minus a multiplied by 4 and divided by alpha. Right, hopefully that's how it's supposed to go, right? So that's basically what we wanted. It actually makes sense, right? So and then we want to divide all of that, you know, 1 by all of that, like so. There we go. So that's basically sigmoid, right? That's essentially sigmoid. So it would be kind of interesting to look into that sigmoid, right? So this is the alpha, and the alpha, if I'm not mistaken, right? Alpha. We can pick one of those alpha in here. So one of them is 0, 28, right? So this is alpha n. And the alpha m is 147. But I'm not really sure which one we have to use. So it's kind of... right. So alpha is the abruptness of the change of the sigmoid. Alright, but why do we have two of them? Right? And how do I plug alpha n and alpha m into this sigmoid? So I don't really know still. This is a good point. Wait a second. I think alpha alpha n is used in the n integral and alpha m is used in the m integral. But we don't use sigmoids in an integral. We just don't. So we first compute m and m, we normalize them from 0 to 1, and then we plug them into S, which accepts both n and m. And that's it. So I don't know. Equations 1 and 2. I don't think it makes sense to me. Right, I didn't see where a sigma plays a role in here. There's no sigma in here. F, if I understand correctly, it's basically the state of the grid. Right, it's the state of the grid at particular point at particular time. So there's no sigma in here. So it's just like we just sum those things up. Sigma n and sigma m. And here's the thing. There is only sigma m. There's only sigma m. There's no sigma n defined anywhere in here. So that's the problem. Like, I read this paper, I don't understand where they come in place. So yeah, because of that, I'm going to you can always read this paper, by the way. It's very small, and feel free to read it and point out like what is sigma n and sigma m to me. I freaking know. So if they literally just used alpha n and alpha m somewhere here in the definitions, it would have made sense to me. There's no sigma n anywhere. Like, guys, you're talking about sigma n, there's no sigma n. That's the problem. There's no sigma n. At least I didn't see it. So I think chat just like... People who tell me things, did you read the whole paper first? Or are you just like, yeah, whatever. Sigma, there's no such thing. Sigma 1. Okay, so there is a sigma 1, there is sigma m. There's no such thing as sigma n. It literally does not exist in the entire paper. It's not a thing. It's not a thing in a paper. There is sigma m. It's mentioned 3 times. There's no sigma n. So that's the problem. That's what I'm talking about. Guys, that's exactly what I'm talking about. It's confusing. What the fuck is going on? I don't know. Maybe I'm dumb. Right. My guess is sigma 2 is supposed to sigma n. Probably. That's a good guess. So that means there is a mistake in a paper. Right. Is there any way to see, like, is there errata date or something like that? I know that RFCs have errata section where, like, you can submit things and stuff like that. Is there something like that in here? Probably not, right? Errata section in RFC is actually very useful, right? So when you're reading the RFC and you notice some bullshit, you can just always open errata, and there will be something there that actually could, like, explain that. Errata for paper is usually another paper. Oh yeah, okay. So actually, I never wrote scientific papers, I think. Well, I mean, technically I did, because that's what was part of what, like, studying in university meant, but I mean, I never took it seriously. It was never anything useful. So I think... Yo, I think I remember, I think one of my open source repos were referenced in a scientific paper. I think. Yeah, let me actually find that. So one of the repos in Otsonic organization, it was in OCaml, and it was for Convex Hull. Convex Hull. So essentially what I did here, I implemented the Convex Hull algorithm in OCaml, right? And it was 7 years ago, by the way, right? So it was 7 years ago I implemented this entire thing. And somebody referenced this thing in a scientific paper where they were trying to automatically, I think, parallelize functional programming algorithms, and this is the only functional style Convex Hull implementation that they could find. Right, so because it's a Convex Hull, but it's implemented in a functional style. So because 7 years ago I was really into functional programming, and that's what I literally did. So yeah, so that's basically it's in a pure functional programming style. I wonder if we can find that thing. Tsoding convex hull. Oh my god, why DuckDuckGo is so slow? Maybe. I wonder if there were some. What is the Google service called for papers? Google. Oh, you guys. Oh, you found that. Thank you so much. I was about to. I think Google Scholar. Yeah, I thought maybe I can search for Google Scholar. Yeah. So let's actually download PDF. Can we download PDF? Yeah, boy. Professional functional languages. And if you search for Tsoding, yeah. Look at that, github.com Tsoding convex hull. But it actually refers to Agner Fog instruction. I don't know what the hell is that. And it's actually, I think I was mentioned like twice in there. Because, so this is the proper credit, right? So Tsoding 2015 convex hull. Right, so isn't that cool? I have nothing to do with scientific world, with computer science or anything like that. I was just like, I'm just shit posting on the internet, right? So I was just doing things on the internet and it was just like citing in here. How did you learn about it? I think somebody who read this paper went to this repo and then found our Discord server, and they joined the Discord server and they asked question about this paper. I think they thought we had something to do with that paper because we were actually like quoted in there or something. This is how we found out. That's so cool. Right. It's kind of strange. Like I would never expect something like that to happen, but apparently I was the only one like who implemented convex hull algorithm in a purely functional style, and they needed that for their testing, for their technique of prefetching, that's supposed to speed up the pure functional programming algorithms, right? So they were basically researching that. So if you program in pure functional style, can you get the same like performance as like imperative style? So they were just basically developing techniques for speeding up this kind of stuff, right? So yeah, that's actually kind of cool. Yo, am I a scientist? What the fuck? Did you read the paper? No, I'm not a nerd. Why would I read that? Maybe I should, by the way. Maybe I'll read it at some point. Maybe I can make a stream about like this kind of stuff and just looking into this technique. Implementing functional convex hull is a shitpost? For me, yes. Because that's what I used to do for fun 7 years ago, and it's just like, yeah, I would just take a random thing and just implement it in a pure functional style because, haha, funny function applications. Just for me, it's a shitpost. I don't know. I still do not take it seriously, to be fair. For me, functional programming, pure functional programming, is still programming in a funny way, right? It's just like you're doing funny things. Okay, Tom Cass, thank you so much for Twitch Prime subscription. Thank you. FP stands for funny programming. Exactly. Anyways, so let's actually continue, and we were implementing Sigma balls. Right, and we've got this entire thing. So let's go with a Sigma 2, right? Float X, float A, float B. Right. So, and what are we doing here? We use Sigma 1, 1xa, and multiply by an inverse of a Sigma 1. So it's basically, it's a derivative of Sigma 1, but it's actually not particularly derivative because this is a different Sigma. The derivative of Sigma 1 would be actually something like this, but since we put B in here, it's not particularly derivative, so yeah. So it's something else. It is something else. Okay, so this Sigma 2, and the next one is going to be Sigma M, and this one accepts X, Y, and M. Right, so this one is a little bit more complicated. So we take X multiplied by an inverse of Sigma 1, M half, right, so I don't really know what that means, but then M multiplied by sigma 1 m05. Hope I didn't make any typos in here. Looks good. I suppose this is literally the same thing, right? So this is literally the same thing, and this is sort of like an inverse of this entire stuff. Okay, so that like looks okay. Okay, and float s, this is the final thing, the final boss of the proprietary function, sigma 2 n sigma m b1 d1 m. So, and as far as I know, b1 b2 d1 d2 are the birth and death intervals of this entire thing. So at a particular intervals you basically become either dead or alive and stuff like that, and it kind of corresponds to like a generalization of the Conway's game of life rules, right? If that makes any sense. Right, sigma, so b2 and d2, and effectively we just return this entire thing, right? So we just return this entire thing, and we need to define the parameters b1, b2, d1, d2, and they are given at the end of the paper yet again with all of these parameters in here. So we can just yoink those parameters, right? b1, b2, d1, d2. So we're gonna put them in here, right? So b1 0278. So I suppose these parameters, they literally played with the parameters and like tweaked them around and just found the ones that look okay-ish. Right, okay-ish enough for a paper. And D2, I suppose, is 445. Right. So that's basically all of the parameters, right? So we have a radius, we have the death and birth intervals, and we have some sort of alpha, right? So, but we still don't know what is alpha n and alpha m, right? So it's kind of weird thing. If we, by the end of today's stream, if we manage to see this little thing, I'm gonna call it an epic win, right? So I'm not sure if all of that shit is going to work, but if we at least see the glimpses of this thing, that's an epic win, right? Okay, so, all right, so let me try to compile this entire thing. Is it going to work? Okay, so it wants a mathematical stuff, so that means we need to include math, right? So we include in math, and also we need to link with math. You need to think like math. You need to link with math. There we go. So this is what we got. That's pretty epic. Okay, so we have this mathematical function, and we can kind of feed that shit into this thing now, right? So if I do s and m, right? So s and m, and this is going to be effectively equal to that s and m. So the order is nm, right? So the order is nm. That's kind of, yeah, that's weird. Okay. I hope there's no mistakes in here. Right? I really hope so. And it's 0. I suppose this is because, well, sometimes it's, okay, so sometimes it's something. Sometimes it is 0, sometimes it's something. Right, I'm really glad that it's not always 0. Right. Okay, so one of the things we can do, we want to compute this stuff for each individual point of the grid. Right, for each individual point. So that means we need to generalize this entire thing. So how are we going to be computing this entire stuff? So yeah, let me see. So maybe, grid diff, right? Grid diff, and maybe we're going to have this thing as literally like a second grid in here. Right, that actually sounds like a very interesting idea. So this is going to be grid diff, right? And we can say compute grid diff. And in here, what we need to do, we need to just like do this entire thing for each individual point. So we're going to wrap this entire stuff to a loop. Right, so but here the parameters of the loop are going to be cx and cy. So we're going to do int cy 0 less than height. So that's the first sort of layer of the loop. And then cx less than width. plus plus cx. There we go. So I'm going to just close this entire thing. And then we're going to close this entire loop completely, right? So, and we're basically doing that for each individual thing in here. Right, and inside of this thing, we're going to be calling, so once we're done with this thing, we can do S, N, and M, and we can apply it to grid diff, right? We can apply it to grid diff for CY, CX, right? For CY, CX, we can just put it in here. And what I want to do, I want to actually print this entire thing, right? So we already have a function called display grid, but it's actually hard-coded to accept that global grid in there, right? So that global grid in there. So maybe what I want to do in here, I want to actually accept sort of like any grid of height and width. Yes, I know that it's going to decay into a pointer to a grid and not an actual array. I do that intentionally for documentation purpose, right? I know, because there are people like that gonna be, you didn't know that it's decaying. I know, I do that intentionally. Because I've seen that too many times, I'm sorry. So, right, and in here, what I want to do is essentially, I'm gonna put a grid in here, right? So I'm just gonna run this entire thing, right? And that's basically the state of the grid, right? So this is the state of the grid. So what we can do compute grid diff, right? So we're computing grid diff, and we want to display grid diff after that, and we're gonna be using the same trick. We're gonna use the same trick for displaying the continuous value of this thing, right? So let's see if it actually produces anything. It's taken, the values are rather small, right? So they're not really telling us that much, right? So because I presume they are too small. One other thing I want to do in here, right? So I want to make it like 10, right? So something like 10. And let's actually display them as floats, right? Because maybe they're so small, there's no point in displaying them like an actual things, right? So because that's what it feels like, at least to me, right? So let's take a look at their actual values in here, right? So this is the size t x0, x less than width, plus plus x, f, and grid diff y x. Hope I didn't do any oopsie doopsie and potential fucky wucky. Okay, looks good. So we probably want to put space in here and then a new line in there, and let's see what we got. They're really small, believe it or not, they're super small. That's very interesting. So yeah. Let's take a look at what people say. I've been reading an implementation in MATLAB that uses those sigmoid function, and it looks like they use alpha n and alpha n in sigmoid 2 and sigma m respectively. Could you please point at the MATLAB implementation somehow? So I would like to take a look. And I really want to know, is that a mistake in the paper? Is that a mistake in the paper, or it's just like I cannot interpret that properly? It's just like so weird because it's like confusing and misleading. So I don't know. Okay, so and what essentially you can do, it's on the oh, you have to download it. Yeah. Okay, so this is sort of like one of the implementations, right? We can take a look at it if we don't manage to come up with something working. There's also Python version that does the same thing. Huh, weird. Okay, so we can try the actual thing in here, right? That is written in a paper, right? That is written in a paper. And then if it doesn't work out, we may take a look at the Smooth Life implementation, right? So somewhere here, right? Okay, so let's continue. All right. So one of the things we want to do, so we also define a delta time, right? We also define a delta time, so basically the time step that we use to simulate this entire thing. I wonder, do they specify their time step? So the smooth glider, they don't really specify their time step, so it's okay, I guess. So for now, I'm gonna specify it as just like 1, right? And we can increase it in the future, right? So we can increase it in the future. So the way you're supposed to update your grid, the way you're supposed to update, if I'm not mistaken, is just like grid yx, right, plus multiplied by dt, right? So that's basically what you have to do. And I think they even mention it. Yeah, there we go. So that's basically the formula, which that's basically what it means. But if you want to do it like that, you actually have to remap the value s from the range from 0 to 1 to the range of from -1 to 1. So multiply by 2 and like this. And this is something we can try to do automatically in the compute grid diff in here, right? So we can basically assign like a value in here, so let's call it q, right? And when we're assigning the diff, we're gonna do 2q minus 1, right? So that's basically what they want us to do in here, right? Specifically in here. So that makes sense to me, and that makes it super easy to just do this kind of stuff, right? So okay, let's try to display the grid. So this is going to be the grid. This is our grid. So we compute the grid diff, then we sort of apply the grid diff, and we may want to take a look at the next state afterwards. Since the diffs are so small, I feel like it's not going to be visible right away on the second iteration, if you know what I mean. Right, so let me see if it's going to work. Okay, so it became, what the fuck is this shit? What the fuck? How it's okay, so it overflew apparently. It overflew apparently. Do we have to clamp? Yeah, okay, so this one is kind of dangerous, right? Because I feel like the result of addition has to be clamped to 0 and 1. But it's not really mentioned in here, because the values of the cells are supposed to be from 0 to 1. What do you guys think? Should we clamp? What's big S? I also don't know. This is the second thing that I couldn't understand, right? So they say, if we think of the application of S and M as nonlinear operator S, we can write this. But what is S? It's just like, they say it like, it should be obvious what S, it's a nonlinear operator, like, bruh, like, it's just like, it's a nonlinear operator. They never define it in the paper either, by the way. They never define it either. So this paper has two mysteries for me. It's alpha N versus alpha M and big S. It's just a name. Okay, cool. I understand that it's just a name, but which nonlinear operator? Can you show an example of what kind of, like, what exactly do you mean by that? It's just like, what? Calculate a send for every point with the old function value, then set it to the new value. Yeah, I guess. So do they want me to put a sigmoid in there or what? Like, it's just... I don't know. I'm not a mathematician. Just ask ChatGPT. You won't believe. I did. It couldn't come up with a proper answer either, so it couldn't understand what the fuck it's talking about as well, so... Right. Big S is simply a function which gets you from x to a small s and f of x. Okay. Oh, okay. This one makes more sense. This one kind of makes sense actually. The sum of, yeah, smaller s's. So yeah, if s is something small, but then I don't know, man. It's like weird and confusing. It is weird and confusing. So I'm gonna just assume that you can basically multiply it by that, like so, and this can be fine. So let me see what kind of stuff we get in here. Right. So so there we go, and all of them are 0. That doesn't make any sense because I didn't do grid Y, grid X. Okay, and they became instantly negative, which is kind of sus, not gonna lie. So if I take a look at the grid diff in here, right, if I take a look at the grid diff in here, they are, yeah, so they mapped really badly in here. So that's really strange. And okay, in that case, that makes sense to have a very small dt, right, around like 1. Because in that case, if you multiply by that small dt, right, so that's what you're subtracting actually, right, so that's what you're subtracting. And if you take a look at this thing, it makes sense more or less. So, but I feel like we still need to clamp this thing, right? So one of the things I would like to do is just clamp it to this kind of stuff. Can I have something like, I remember that John quite often defines a function clamp, which actually accepts the pointer of this thing that you want to clamp, which I found very useful. Right, I think it does in fact make sense to do it like that. So we have a value, then you have lower and high, right, and essentially if x is lower than L, it becomes L, and then if it's higher than H, it becomes H. So that's the whole thing. And it's just like, to be fair, like clamp that modifies this thing like a little bit easier to use. But they say it's from -1 to 1. Who from -1 to 1? The function f. So yeah, so we redefine s to be from where we have defined a new s that has values in the range from -1 to 1 instead of 0, 1. Is the translation function? Yeah. So I think that's what we want to do. Let's give it a try. Let's give it a try. So, okay. Okay. Did we get something? I think it changed. But we don't see the new line anywhere. So let me put this kind of thing in here. Okay, it changed. Look at that. It literally changed. So there was this thing, and now it's completely different. Okay, so let me try the following thing. I'm gonna make the size of this stuff bigger. Maybe not that big, but we can make 20 by 20. And let's try around maybe 10 iterations. By the way, in a compute grid diff, do we reset? Yeah, we do reset this entire thing, so I don't need to clean anything up. Right, so, and let's try to, like, do this 10 times, right? Can we do that 10 times? Compute grid diff, apply grid diff, and display grid diff. So maybe this thing should be a separate operation as well, if you know what I mean. Right, maybe it should be a separate operation as well, and, okay. It was just like, you know, blinking or something like that. I wonder if I can make dt even smaller. Is it going to... I was doing something. All right. So let me go to here. All right. Cool. And maybe one of the things we want to try, we actually want to make it infinite, right? So let's actually go indefinitely and see how it's going to go. Maybe it will do something. Yeah, I just wanted to... All right. Is it doing something? What the fuck? I think it's doing something. It turned into a square. That's cool. Well, it started doing shit. I mean, that's already something. What about like making this entire shit bigger, like 100 by 100? Right, but I feel like it's just like it's not gonna. And it's taking too much time to. Maybe this is because the neighborhood is too big. Right, I don't know why it takes so much time to... Let's actually try to optimize like all three. Maybe that's what we need to do. Okay. The fuck? This is magic, like holy shit. Why are they not moving though? They're kind of moving, but they're settling at something. Is that basically smooth life? Also, it's not really squarish, right? So it's not really squarish. One of the things I may want to try to do. Okay. So when I display the grid, let's actually print it twice, right? So maybe twice. What if I use fputC instead of printf? So maybe that will speed it up a little bit, because I know maybe printf is too slow. Right, and well, this is supposed to be std out in here. I want to do something like that. I'm not sure if it's going to affect anything. But, right, so I want to make it sort of squarish. You know what I mean? So it creates static structures, which I'm not really happy about. So what's the size of the radius? So can we just make it like 11? And what if we make it smaller? That's okay, that's very cool. Smaller radius actually creates this kind of... It does look like original thing, but it's not really doing anything interesting. Right. Okay, one of the things I want to try when I do a random grid, let's actually not initialize the whole grid. Let's initialize like a half of the grid. Right, so what if we initialize half of the grid? Okay. It's kind of expanding, it's kind of doing things. This motherfucker is that a glider or something? Okay, can we make it move faster? What's the DT? DT might be actually too small. Let's make it bigger. It's fucking moving. I think we have something moving in here, like a glider or something. It's a stable structure that is moving. Well, I mean, it's... What the fuck? This is so fucking cool, holy shit! What the fuck? Did we do it? And then it goes into this like a stable state and it just sort of dies out. That's so cool. That is so fucking cool, holy shit. Right, so... Okay, what if I initialize that with even smaller thing? What if I initialize that with even smaller thing? This is a this motherfucker is this is a glider. Oh, it starts to divide into two. When it... And it goes into this stuff. But the original thing had Radiate 21. Right, it had a Radiate 21, so... in this case it actually just dies out. So it's kind of like a too much for our small thingy. What if I change the alpha, right? So what if we use the different alpha? Yeah, didn't work out. Rand. Where's the random? Let's do half. Okay. Alright, I suppose this combination of parameters kind of worked. This combination of parameters kind of worked. And it created interesting structures. You know what I would like to do, probably? Actually, maybe center this entire thing somehow. So we can just do something like width, which is this thing divided by 2, and height divided by 2 as well, right? And let's say that I'm gonna be iterating through this entire stuff, but this is gonna be not y, it's a dy and dx. dy, dx, dx, right? So in an actual x and y is gonna be basically x, half of the width minus half of that thing. So it's gonna be sort of like centered, so we can see, because it's down on the edge, and so it's kind of difficult to see what the hell is going on in there. All right, so you know what I mean? So let's actually try to do something like this. So, yep. It didn't do shite. The fuck? Excuse me? So I suppose it has to be actually, yeah, minus dx plus and dy plus this entire thing. Okay. So let me see. There we go. So it's at the center at least. Now we can see that from the center, and I want to keep making it smaller, maybe. Right, what if I divide that by 4? So this is going to be like 1/4 of this entire thing. We could try to maybe initialize that with a circle. So, yeah, maybe circle would have been actually very interesting. But how can we even do this kind of thing? We can just iterate through the entire thing. So this is going to be 3. So did it recompile actually? I don't think so. It's 2 of them stuck together. That's cool. And they're moving. So I suppose it's you basically need to come up with the parameters that make it just like more stable, because I want to be able to see like a single things in there, right? But it does look like the simulations, like the animations I've seen online. It does in fact look like one of the simulations that I've seen online. And once it gets into that state, it's just like pointless to do anything. It's just, it's a very stable state of this entire thing. Some things may actually happen in here. Some things are actually happening in here, but it's kind of difficult to get out of that state, you know what I mean? Right. So, and maybe it would be nice to maybe get like a correct implementation, because I was just following the paper as it was written, as I understood this paper, right? As I understood this paper. I don't know if I'm just smooth-brained, like this game of life, just it's a smooth life, maybe my brain is as smooth as this life, or there are some mistakes and typos in this paper, so I don't really know. So, so if whoever watches that, maybe like on YouTube in the future, maybe just like in the chat, tell me that what kind of mistakes I've made. So it's kind of important for me to know, like, is that my mistake? Is it me who's being dumb, or is something wrong with the paper, right? But at the end of the day, it kind of worked out. If we just plug these things into this thing, it does in fact create these kind of cool structures. right, so, but I'm too dumb to understand why and how to do that thing properly. But I tried, and it's actually fun, right? So, should I do more of this kind of series where I just like take some paper and just try to implement that? Not something that is difficult to implement. I definitely won't be able to implement the sparks of general intelligence, right? Because I don't have hardware for this kind of shit, but you know what I mean. Right. Project order search, I think I already done that, but I don't know. So yeah. Right, so let's actually do a committee. Right, so this is basically my interpretation, so I'm gonna release it under MIT. And by the way, I'm gonna actually like put that on the GitHub. Feel free to submit pull request, and in pull request explain me what I got wrong, and please also tell me, is that me being dumb or is that something wrong with the paper? And if it's me being dumb, please tell me where they refer properly to alpha N and alpha M. Right. So it's just like it bothers me so freaking much. It's just like I don't understand. Yeah. So readme. Okay. So this is a Smooth Life implementation by Smooth Life implementation in C. Right. So this is going to be quick start. And the quick start is very simple, right? So I didn't overcomplicate anything, build.sh, and then you just run this entire thing, all right? And then we can do references, right? So the references, and the reference is basically this paper, right? So we used only this paper. We didn't cheat or anything. We didn't look up any of the existing solutions. I just followed this paper. Implementation, okay. All right, so, and let me do git ignore. I want to git ignore the main. There we go. And can I do git init? Right. So, ready, set, a go. Yo, what if I implement Smooth Life in a purely functional style? Would I get credited in another 5-hat scientific paper? Yo! Easy citations, farming citations, just like taking all of the, like, you know, famous algorithm and just implemented them in a purely functional style, and you just farming, just fucking farming citations. Easy. Freaking Erdos number increasing. Oh, that's what it's called. I was trying to remember. Like there was some sort of like a metric for how good of a scientist you are, for how many people you manage to debate to read your paper. Smooth Life. Okay, so right. So do Smooth Life implementation in C. So this is going to be public, of course. We're not gatekeeping shite. We're making everything public, and I'm going to what? I'm going to git remote add origin and this. I thought I copy pasted this entire thing. I said copy paste. There we go. And let's push that right into the repo. Right into the repo. Is it pushed? Is it pushed? It's not even pushed yet. Come on, you can do that. All right. So here it is. Here's the result of today's stream. So let me go to the description. So this is the source code. There we go. That's pretty cool. Let me take a look at that one more time. So that's the result of the... It was one... First it was glider, and then it was a pulsar or thingy like that. It was actually the thing. The legend. I heard the legend of about the structures. Yes. Well, what's interesting is that it forms these strips, and all the strips feel like basically several gliders stacked together side by side. Does it feel like it? Because it basically consists of these gliders. That's what it does. Right. It's kind of weird. Right. Well, this one didn't really work out. Wow, this one is interesting actually. What is gonna like blow up? Is it gonna be single? This is a single glider. But they're not stable. They're not stable enough. I think we need to come up with a set of parameters that actually makes this entire stuff stable. Right. Yeah, so here you can see, so the two gliders like trying to separate from each other, but as they separate, they actually multiply. Right. As they try to separate, they actually multiply, and at some point they get into the state where it's just like stuck and there's only strips of just like this stuff. Yeah. All right. Okay, so I think I need to acknowledge all of the people who were throwing money at me. So I think I already acknowledged Tom Cass. Thank you so much. Paul Octaviank, I hope I pronounced your name correctly. Thank you so much for tier 1. And Above Par Nonsense, thank you so much for Twitch Prime. Thank you everyone. I'm already streaming for 2 hours, and this is usually my usual time for streaming. So I guess that's gonna be it for today. Today was actually a fun stream, right? I actually didn't, like, the only thing I did before the stream, I just tried to understand the paper, right? I was trying to understand the paper. I didn't really know if it's gonna work out or not, right? I just wanted to see what's gonna happen if I just like code it as I understood it, right? And I was kind of skeptical, to be fair, at the beginning, because I didn't understand some of the things. I didn't understand the alpha thing, and I didn't understand the linear operator. But I'm surprised it just like produced something. I'm surprised it produced something, but that dies out, of course, right? So, all right. Yo, this is a glider! And it dead. Okay. All right, that's it for today. Thanks everyone who's watching right now. I really appreciate it. Have a good one, and see you in next. Love you. Mwah.